In the last lesson, we left off with the bright line spectrum when we said that certain elements will produce certain colors when you put them through a prism. And Niels Bohr went on to find that those absorption and emissions of lights by hydrogen corresponded to the energy changes of the electrons within the atom. He proposed that the electron is able to only travel in certain orbits, and Bohr calculated those and found the energy difference, predicted which wavelengths those lines would show up. The problem with the Bohr model was that it only worked for hydrogen, and so they went further on to figure out what's going on in the electron. The ground state of the electron, of course, is the lowest level of electrons, the lowest energy level. Sometimes, especially like with the photoelectric effect, the energy can be absorbed by the electron and it can jump up to an excited state, and that is the higher energy level that it absorbs. And of course, whatever goes up must come down, and so when that electron falls back down and releases the energy, it releases it in the form of a photon. So it absorbs energy to go from the ground state to the excited state, but it releases energy to go from the excited state back down to the ground state. And so here's an example of those falling down to the different energy levels, and that's where that energy calculation can be determined based on the wavelength from one energy level to another. The wave mechanical model was Schrodinger, and he's famous for his famous cat. If you don't know what that is, I invite you to look it up. And de Broglie worked on a wave mechanical model. The electron is visualized kind of like as a standing wave, or opposite of a traveling wave, and this is our modern view of the atom. So we said that there's an orbital, which is the wave function. There's a fancy equation called Schrodinger equation that you can actually calculate to figure out the location of the electron, but luckily we don't have to do that. Guy by the name of Werner Heisenberg came along, and he gets his name on a principle to state that you can't know something. But he's saying in this principle that you can't know both the location or position and the velocity or momentum of a particle at a given time. And so he got his name put on that. So the accepted definition of the size of the hydrogen 1s orbital is the radius in which 90% of the electron's probability is to be located. So when we're doing electron arrangement, we're at 90% probability of where that electron is located. So we're going to be doing electron configuration. Hopefully, once we go through it, it'll be a review from Chem 1 where we did that. So here is just a visual of the distance from the nucleus and the probability of finding that. And that distance from the nucleus, r, is going to be important with Coulomb's law later. And then, of course, we know that our electrons are arranged in an atom in a series of levels and sublevels called shells and subshells. That's where those S, P, D, and F. The energy levels are your first one. As you go further out, 1 is less energy than 2, which is less energy than 3. And they get not only larger, but higher energy. So the further away from the nucleus that something is, the higher energy level it's at. And then, of course, each energy level can hold more electrons. For instance, energy level 1 can only hold 2. Hydrogen and helium fall in there. Energy level 2 and 3 can each hold 8 electrons. And then after that, we can start holding more because the d orbital kicks in. So here are our 4 types of sublevels, applying to the electrons in their ground state. The s orbital, which has 1 orbital or 1 orientation around the nucleus. It holds 2 electrons and it is spherical shaped. The p has 3 orbitals, which correspond to 3 orientations around the nucleus, can hold 6 electrons, 2 electrons in each orbital. The d has 5 orbitals and it holds 10, again, 2 electrons in each orbital. It's kind of a daisy shape. Basically, it's 2 of the p orbitals put together like a dumbbell. And then the f orbital has, f sublevel, has 7 orbitals and holds 14 electrons. Again, each orbital holding 2 electrons, so 7 times 2 is 14. And it's called fancy shape or complicated sometimes. When we're talking about the quantum numbers, remember that's the address or the location of an electron. So the 4 quantum numbers tell you the address, or I would like to say location, of an electron. And we did quantum numbers in pre-AP. We did not do them in regular. The good news is in AP you do not have to assign quantum numbers, but you do have to be able to understand them and know what they mean, but you don't actually have to give them yourself. Kind of disappointing. I think quantum numbers were pretty easy, but you don't have to. But you do have to know what the 4 quantum numbers are in terms of their definitions. So the first one is the principal quantum number, and that tells you what energy level you are in. Remember, as n increases, you have higher energy, which means you have a larger orbital, and you're farther from the nucleus, or farther from the nucleus. Sorry, used the wrong word there. The azimuthal or angular momentum, I usually always call it angular momentum because I can't say that word. In Chem 1 we used angular momentum. It's referred to as L. They are the values of 0 to n minus L, and that is the shape of the atomic orbitals. And it's also telling you, basically when I say shape, it's telling you whether you have S, P, D, or F. Those numbers correspond to 0, 1, 2, and 3. Okay? So those are going to be the numbers that correspond to having S, P, D, or F. 0, of course, is S, 1 orbital or 1 orientation. The p orbital has 3 orientations around the nucleus. The D has 5, we already said this, and the F has 7. So here is a p orbital, so this would correspond to those 3 orbitals that each hold 2 electrons for a total of 6. This is the D, and it has 5 different orientations or possible locations. Again, each one of those holds 2 electrons for a total of 10 electrons. And that's the F, okay? And F has 7 different orientations. And when I say orientations, if you haven't noticed that, these are 3D shapes, so there's an XYZ axis that we're talking about these orientations around the nucleus. And each one of those orientations can hold 2 possible electrons. The magnetic quantum number, which is M sub L, is telling us which one of those orientations is it in. So which one of those pictures is it in? And we call that, the value is negative L to positive L, including 0. So for instance, we said if you have a p orbital, your L value was equal to 1. So your M sub L value is, we'll draw those as the 3 orientations, and we start negative 1, 0, and 1. If we had a D, we said D has, the L was going to be equal to 2. So then has 5 orientations, so we have 5 lines, so we'd say negative 2, negative 1, 0, 1, 2. And that's just our way of keeping track of what orbital would it be in, and that way everybody's doing it the same. Your spin quantum number is the easiest one of all. It's telling you the direction of the spin. It's 1/2 or a negative 1/2. And we'll find out when we get to the rules of electron configuration that when electrons are paired up, you probably remember this from Chem 1, they have to be spinning 1 up, 1 down. And so when we show that, we say half, positive half, negative half for the down. Okay, so that's how we represent that. Because the reason they're not traveling around together, 2 by 2, like Noah's Ark, is because of electron-electron repulsion. And so they spin in opposite direction to minimize that. Orbitals have regions of high electron probability. We call them areas of 0. Sorry, I'm totally lost my train of thought there. I apologize. Start over. Orbitals have regions of high electron probability and regions of 0 electron probability. The areas of 0 electron probability we call nodes. So there we have some pictures that show that. So in those nodes are the most likely area where we would not find an electron. The degenerate is orbitals that are equal in energy. So all 3 of the 2p orbitals are degenerate, meaning they all have equal energy. If I was in the 3D, say I'm in the 3D orbital, all 5 of those would be degenerate, meaning they have equal energy. Pauli exclusion principle is going to be the first thing that we look at when we're talking about how do we put these things, or how do we do our electron configuration. And it states that an atom in an atom, no 2 electrons can have the same 4 set of quantum numbers. So basically what that means is that's why they have opposite spin, because they might have the first 3, they might be all in energy level 2, they might be in a p, and there might be 2 electrons in the p first position, but one is going to be spinning up, one is going to be spinning down, so they would not have the same 4 quantum numbers. The Aufbau principle states that electrons enter the orbitals of lowest energy first. In the ground state, atoms have electrons in the lowest energy order. Here is the order in which it fills. Is 1s, 2s, 2p, 3s, 3p, 4s, 3d. Notice that that is where it drops down right there, and that is because it requires less energy. Even though it's in a higher energy level, it requires less energy to fill a 4s, which only takes 2 electrons, than it does to fill a 3d, which takes 10. And then you go on to 4p. You do not have to memorize this particular order, because I'm going to show you, if you don't remember, I'm going to show you how you can do it based off the periodic table. Okay? Hund's rule is the rule that states that everybody, all orbitals have to have 1 electron before they get another one. So all orbitals will be half filled with electrons having parallel spins before they are completely filled. So what that means for us in a nutshell is everybody gets an up before they get a down electron. And you may remember that from first year of chemistry. All right, so we're going to look at our periodic table. We're going to review these relationships. I have given you a handout that has this on there for you, so you can look at that, or you can look at the one in the notes. But this is the order that they fill. Okay, so when we're reading this, we read it just like we would a book. So we start at the beginning and we say we fill up the 1s's first, and then we come and we fill the 2s's, and then when we're done with that, we come over here and we fill up the 2p's, the 3s's, the 3p's, the 4s's, and then we fill up the 3d's, then we start filling up the 4p's. Okay, so they do that. Here is where it takes a little bit of a roadblock. This is lanthanide and actinide. Where these fit in are right here. If you notice, if you look at the big periodic table in the classroom, this is element 57. If you look right next to it, hafnium jumps to 72. That's because down on the bottom is 58 through 71, and these are filling the F block. So if we're coming along and we're filling this up and we get to here, we got to take a detour and go to pick up our F block, and then we come back up to fill the D block. Okay? You'll notice that the D block of the periodic table is always n-1, meaning 1 less than the period number, and then these are always n-2, 2 less than the period number. Before we do the exceptions, let's do a couple of electron configurations and see if we recall how to do that from Chem 1. All right, so let's do some easy ones. We'll start with carbon. If we look at carbon, it's got 6 electrons. So we go across and we say we fill up 1s2 first. Then we go to the next line and we fill up 2s2 next. And then we go over and carbon is in 2p, and it's the second slot, so that means it has 2 electrons. The way we would draw the orbital diagram or the orbital notation for that is we'd say 1s, 1 up, 1 down. Then we go to 2s, and then we'd say 1 up, 1 down. For 2p, we would draw 3 lines, and we only have 2 electrons to put in there, so we're going to say 1 up, 1 up. Those are arrows. They're half arrows because I'm lazy and they're faster to draw. But remember, each arrow is representing an electron. They're not number ones, they're arrows. It takes longer to draw the whole thing. Let's do oxygen, which is 2 over from that, so it has 8 electrons. So 1s2, 2s2, 2p4. if we were to draw it, it would say 1s, 1 up, 1 down, 2s, 1 up, 1 down, and then 2p. Needs 4 in there, so we're going to say 1 up. We're going to fill everybody with an up before we fill with a down. And that's how we would do that. Okay? Let's do a couple of more complicated ones. Let's do my favorite element, vanadium. Let's clear that. So vanadium has 23 electrons. If I look at where vanadium is located, okay, I can see that if you look at the big periodic table in the classroom, it is the third element in the D block, and that is 3D. So it's going to end in 3D3. So basically what I want to do is I want to do my electron configuration and stop when I get to 3D. So I would say 1s2, fill that line up, go to the next one, fill up 2s2, 2p6. After 2p6 comes 3s2. Fill those up. I'm going to fill up my 3p6. Then I'm going to fill up 4s2. And now I'm going to fill up 3d3. If I was going to draw that in orbital diagram, 1s, up, down, 2s, up, down, 2p, up, 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 down, 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 3s, up and then down, 3p, give everybody an up before you give them a down, and then comes 4s, up, down, and then comes 3d, which has 5 orbitals, but we only have 3 electrons, so we would draw it like that. So that's what its orbital diagram would look like. Okay, so now that we've practiced that a little bit, we'll talk about the exceptions. Now, in Chem 1, I made you memorize the exceptions. You don't necessarily have to memorize the exceptions, but you have to be able to explain if they were to show you this, like instead of what you expect, you get this, you have to be able to explain it. And I have the exceptions marked on the paper that I gave you. Chromium and copper in period 3 are exceptions, period 4. In period 5, molybdenum and silver are exceptions, and gold is also an exception. Actually, tungsten, you would think that it is, but it is not. It's not listed as one of the exceptions. But basically, you expect copper, if we're doing this configuration that we were, going in order, we would expect it to be 4s2, 3d9, but it's actually 4s1, 3d5. So basically it borrows one of the 4s electrons and throws it in the d to complete it. And that is because fewer electrons are sharing orbitals. They're half filled. And in Chem 1 we said that they're more stable when they're half filled or completely filled, but that's not a good enough explanation in AP Chem. So you actually need to say, because fewer electrons are sharing orbitals, electron repulsion is decreased and stability is increased. Here are 2 of those exceptions there, and then I told you the ones below that as well. This is how we draw orbital diagram. We're going to draw it with arrows. Please don't draw the boxes. First 2 pair of electrons, you don't give anybody a down until everybody has an up. Remember that. So they have to have the same spin before you give them a second one. In Chem 1, we called that the empty bus seat rule. If you don't remember what that is, we can talk about it later in class. Okay. Here's an example of the way that they'll ask electron configuration questions in AP Chem. We have 1s2, 2s2, 2p6, 3s2, 3p3. Atoms of an element X have the electron configuration shown above. The compound most likely to form with magnesium is this. Okay, so first of all, if we see this right here, how many valence electrons does it have? It has 5. So it has 5 valence electrons. Okay, and then because it has 5 valence electrons, we know that magnesium has 2, and magnesium likes to give it away, and this one likes to take in 3 electrons, right? So, oops, sorry about that. So if I've got magnesium, as a +2, right? And then this element X has 5 valence electrons. It's going to take in 3, so it's going to form a -3. What is most likely this compound going to do? It's going to be Mg3x2. So this would be the most likely compound, okay? Because we're going to balance out those charges. And basically we crisscrossed. Remember that? Crisscross, butterfly method. Okay. Here's a couple of questions. We got these answer choices. Which one of these would be an impossible electron configuration? So we're going to look at the first one, 1s2, 2s2, 2p5. I think we found our winner on that. That would be impossible because we have to completely fill that with 6 before we go on to 3s2. A ground state element configuration for the atoms of a transition element. If it's a transition element, it's going to end in a d orbital. Okay, so that answer to that one is going to be D, right here, because it ends in that. The ground state configuration of a negative ion of a halogen. A negative ion of a halogen. Okay, so that means, oh, I found another one that's an impossible configuration. I just realized there was 2 on there. Go back to number 6. There's an impossible electron configuration. Which is it? You see it? And that is C. Because there is no such thing as a 2D, right? There is no such thing as a 2D. So the ground state configuration of a negative ion of a halogen would be, which one? Would be B. Because a halogen is going to take in 1, and so that would be B. And then the ground state configuration of a common ion of an alkaline earth metal. And alkaline earth metals are in group 2, so they end in a 4s2, so that would be E. So those are some common ways that they may ask electron configuration questions on an AP exam, especially multiple choice questions. Those are easy, should go be able to grab easy points for electron configuration in your multiple choice questions. Polyelectronic atoms, that's something you might see as a term, is atoms with more than 1 electron, so pretty much that's everything but hydrogen. Silly, seems kind of silly to have it as a term, but it is. Okay? And then this is where we're going to stop, because this is where we're going to start talking about trends, and we'll do that in class.